the two-body problem, well, we've been discussing singular particles our whole lifetime, but the time has come to realize that there is more than one particle in the entire universe. Fortunately for us, unfortunate for our studies. Which means that we have to come to grips with the fact that unlike classical particles, quantum particles are totally indistinguishable. Now, in the moment, if you look at them once, you can say, oh, this particle is in one state, this particle is in the other. We've distinguished them. Unfortunately, if you observe them, you might just be changing their states, which means you can't keep track of which one is in which state over time. It's like if you have a red ball and blue ball and you shuffle them. You can tell that, oh, the blue ball was over here, the red ball was over there, and now they've switched places. But if the red ball constantly changes color every time you look, and the blue ball also changes color every time you look, then, I mean, can you really tell the difference? But it's not just that. While you might be able to follow classical objects, quantum objects, every single time they're observed, because of the uncertainty principle, are going to, well, they might just change their state. There's a probability of them doing so or not doing so, which means you will never be able to know which one is in which. But there is one good thing that comes out of this. Since we now have to update our wave functions in order to make them symmetrical, because otherwise, reality would break down, our measurements would be totally useless, as one could be for this version of reality, another could be for that version of reality, and all the versions of reality created by the differences in permutations of the particles in certain states. By the Pauli exclusion principle, if you have two particles in the same state, the wave function that we constructed just for them to solve the Schrodinger equation, for more info on that, watch the full lecture, is going to collapse. It's going to become zero. And non-normalizable wave functions can't exist in the real world, which means two fermions in specific can never take on, this, two identical fermions can never take on the exact same quantum number. Otherwise, everything collapses. Everything dies. And so, that is what today's lecture was all about. So, there's a very important thing that we have to address. For the past few lectures, we've only been discussing single particle systems. Well, mostly. We did talk about the hydrogen atom. But recall that when discussing the hydrogen atom, we only focused on the electron. We did not focus at all on the movements of the proton, assuming it was stationary. We only focused on the potential that it applied to the electron, which makes this a central force problem. Which is certainly not as difficult as what we're about to address, the two-body problem. So, how do we look at the two-body problem? How is it different in classical mechanics and in quantum mechanics? Well, let's look at it. So the two-body problem is pretty simple. You have, well, it has a simple premise at least. Two masses, M1 and M2. They start with zero mass. They start with zero initial velocity, zero acceleration, and some separated initial position. And eventually, well, actually no, if they start with zero velocity, they'll always collapse into one another, depending on what the force is. So they start with some initial velocity. And so, the two-body problem concerns these two objects. Can we find an equation for the motion of both of them, given the equation of the interaction between the two? Okay, that's a good question. So, how do we actually approach this? Well, in the gravitational case, of course, this in reality depends on what force we're using, but let's just say it's the gravitational force. This force is just C divided by R2, sorry, not R2, the magnitude of x2 minus x1 squared. Actually, that's the force of 1 on 2. The force in the opposite direction is just the negative version. Newton's third law and all that. So, now that we have this, we're going to try and take this two-body problem and reduce it to two single-body problems. How do we do that? Well, by introducing what we call, well, not what we call, you know what it is. The center of mass variable is m1 x1 plus m2 x2 over m1 plus m2. Now, what are we given here? If you look closer, you realize that m1 x1 is x1 double dot is equal to c over x2 minus x1 squared. And so x1 double dot is just this, but it's c over m1. Meanwhile, x2 double dot is this, but it's c over m2. Notice what this means. It means that x1 is almost exactly the same as x2, since both have the same function of t in there. The only difference is the multiplier. One of them has a 1 over m1 in front, one of them has a 1 over m2 in front, which means x1 is just m2 over m1 x2 double dot. Oh, and this should be a negative, which means it should be minus m2 over m1 x2 double dot. And what does that give us here? Well, if we plug in, we get, well, actually, we don't get anything for now. What does happen is if we take the double derivative of the center of mass, you get m1 x1 double dot over m1 plus m2 plus m2 x2 double dot over m1 plus m2. And now we get that since this is minus m2 over m1 x2 double dot, these two cancel out, and we get m2 over m1 plus m2 minus m2 over m1 plus m2 x2 double dot, which means that's right. The center of mass never accelerates. It just drifts off into space. And of course, its equation can be determined from the initial conditions by just taking some ansatz like this and solving for v and x. So we know what the center of mass is going to look like. And then, from that, all we have to do is we've reduced it to two single body problems. Now, we can find the displacement vector of mass 1 from the center of mass and the displacement vector of mass 2 from the center of mass. And now, the specifics of calculating their trajectories comes down to, for the gravitational force, the Kepler problem, which is not the subject of today because we're not going to be talking about classical mechanics for long. We've now seen how to solve the classical two-body problem, which is nice. But, of course, how do we solve the quantum two-body problem? Surely there must be some differences in quantum mechanics, right? Well, the first, of course, the equation is going to look a little bit different. You're going to get this expansion, minus h bar squared over 2m partial 1 squared psi 1 minus h bar squared over 2m partial 2 squared psi 2 plus u, oh, sorry, not psi 1, psi 2. There's one wave function describing both. So, this is what the equation is going to look like. Now, things actually get hugely complicated if we consider the two particles as interacting with one another. which is why we'll save it for next time. For now, what we're going to do is assume the two particles are non-interactive. They just float in space without ever considering one another. Any links are severed. And so, that's obviously not an accurate model of reality, but it can help for approximations, and it can help for our first time looking into this subject. So, if we know that, then what can we do? Well, you might have noticed that at this point, if we remove the interaction term, what do we get? Well, the rest of it is just the Hamiltonian that you would get if the first particle was by itself, plus the Hamiltonian that you would get if the second particle was by itself. Now, of course, there would be that interaction term that would pester us, which means that the actual equation would look a little bit something like this. Let's make that x2 minus x1 squared is equal to E psi. Now, if we set this equal to 0, what do we get? h1 hat plus h2 hat psi is equal to E psi. It is probably very obvious to you now that psi, the combined solution, is just the product of the two solutions multiplied by psi 1 is equal to E1 psi 1, and Hamiltonian 2 psi 2 is equal to E2 psi 2. These would be the Schrodinger equations if each particle was alone in its lonely one-particle system. And so you can probably consider that h bar 1 plus h1 hat plus h2 hat of psi is equal to E1 plus E2 of psi, then that psi is going to be psi 1 psi 2. Of course, you can put that theory to the test. The Hamiltonian of psi 1 psi 2, consider that the Hamiltonian is only a function of x1, which means the psi 2 gets removed, and this just becomes E1 psi 1, and H2 psi is just going to give us the opposite. Psi 1 E2 psi 2 is equal to E1 plus E2 psi 1 psi 2. So as you can see, this was a major success. We know that for non-interactive particles, the two-body problem is just the one-body problem, basically. Now, that's not very exciting because with the gravitational two-body problem, it would also be a one-body problem if these two just didn't know of their existence. It would just consist of two free particles drifting off into space like they would usually do. Just like the non-interactive two-body problem. The non-interactive two-body problem in quantum mechanics is basically the one-body problem. Or is it? You see, quantum mechanics is unfortunately not as cut and dry as classical mechanics. If it was, we wouldn't be studying it. So there's one extra caveat you have to consider. In classical mechanics, let's say I have two objects here. Now, actually, let me make this look more. I'm better drawing squares. Now, even if I have these two, and they look identical, you can comment on, oh, that one's on the left and that one's on the right. Or this one is slightly worse drawn than this one. Or this one was drawn first and then this one was drawn second. Or this one has more area and this one has less. Or this one has straighter lines and this one has more curved lines. Whatever the case, you can always compare these two. Even if they look identical, just paint one red, and suddenly you'll see a difference. Unfortunately, we can't do that in quantum mechanics. Why? Not because two particles are indistinguishable at a glance, of course. Two particles won't be in the exact same place, so you can still say, oh, that one is white and that one is red. This one's on the left and this one's on the right. But here's the problem. You can never keep track of which is which. And that's not just an experimental limitation. Any observation will change the very delicate state of one of these quantum particles. With an ordinary object, if I have a red object and I have a white object and I shuffle them around, you can still tell me where the red object used to be and where the white object used to be. But what if every time you decided to look at them and focus on them, they changed colors? That's quantum particles. Their state changes every time they are observed. It's not that you're not looking close enough. If you look closer and closer, their color is going to change faster and faster. No matter what observation method you use, there is absolutely no way to tell one object from the other because their state constantly changes every time you observe them. So in the moment, you can distinguish particle 1 and particle 2, but so you can say particle 1 on the left here is in psi 1. Particle 2 on the right here is in psi 2. Then you look away and look back. And suddenly you have another one in psi 1 and another one in psi 2. But can you tell me if this is particle 1 or if this is particle 2? No. No observation method you can use can guarantee that your observation did or did not change the value of these two particles' spins or states. So this could be 2 and this could be 1. Or this could be 1 and this could be 2. You have absolutely no way of knowing. Any observation you make, no matter how good, by the uncertainty principle will just change their state. Which means that we've hit a problem. And so we have to come up with a solution. Our wave function must be totally symmetric with regards to state. That is, no matter if we switch which particles are in which states, psi still has to be equal to itself. Because imagine what would happen if that wasn't the case. If psi x1, x2 was not equal to psi x2, x1, then essentially half the time we would be looking at one version of reality and half the time we would be looking at the other. We would get inconsistent measurements all the time, and we'd have no way to know which is which, because of course we can't tell the difference between these two. Which means that there's a difference, but we can't measure it. And in reality, it's not going to be 2, because the universe doesn't have one particle and it doesn't have 2. It has 10 to the 80, which means there are going to be so many different versions of reality, so many different measurements, so many different possibilities for every measurement that are totally inconsistent with one another and the laws of physics that the universe any measurement basically no longer has any meaning. So we want measurement to have meaning, which means that this has to hold true. So if it does hold true, then what? What solutions can we get? Well, for the non-interactive case, for the non-interactive case, there are two ways to do this. You have either the positive way, psi 1 x1, psi 2 x2, plus psi 2 x1, psi 1 x2, or the negative way, which just has the opposite sign. Now you might say, oh, well, wait a minute. That will change sign whenever x1 and x2 are flipped. That's because I was being misleading. In fact, this does not have to be true. These two can be perfectly not equal to one another. Because what actually reflects reality, what gives us the real measurements, is this guy's norm squared. If that guy's norm squared is not equal to itself when the variables are reversed, things go haywire. But that means in practice, the only way it could be unequal to itself is if psi of x1, x2 was equal to minus psi x2, x1, or was anti-symmetric, which is exactly what we're seeing here. So we're all fine if it changes sign. Let's call this psi plus minus. It turns out that for bosons, which are particles with full integer spin, remember that we talked about this, and that just like angular momentum, it could only take on half integer values. Bosons are those particles with integer spins, while fermions are those particles with half integer spins. Fermions, especially half-spin fermions, are the particles that make up the vast majority of the universe. Psi plus is assigned to bosons, while psi minus is assigned to fermions. Now, you probably just observed something really cool. The Pauli exclusion principle. You see, before, we never ruled out what would happen if the two particles were truly indistinguishable at a glance. If they took on the exact same state. So this is in psi 1, and this is also in psi 1. So let's just call it psi. If psi 1 is equal to psi 2, which is that equal to a state psi, then we get that the total wave function, the composite, is equal to psi x1, psi x2, minus psi x2, psi x1. But of course, that's equal to 0. And we all know zero wave functions, non-normalizable wave functions, can never appear in the real universe. Which means that in the real universe, this can never occur. Two fermions can never have the exact same state. Now that's a pretty big deal. Why is it a pretty big deal? Well, it takes a little bit of subtle math to show. So let's get back into the fact that quantum mechanics is a lot about probability at its core. We're about to use that fact to our fullest extent, to the fullest extent possible. So we can find the expected value of some operator, let's call it a hat in this case, by taking the integral of a hat multiplied by some wave function squared over the entire space. So this is how we calculate expectation value. And of course, we can break up the norm squared of a complex number by taking it, well, I should say magnitude, right? Doesn't really matter, or modulus, as psi multiplied by its conjugate, psi star. So now we're going to use this to the fullest extent of the law. What we're going to do is calculate a very important quantity, the expected value of a very important operator, the operator for the distance between two particles, x1 and x2. So you probably already know, this is in 1D by the way, you probably already know that since position is a linear operator, and this expands into x2 squared minus 2x1, or 2x2 x1 minus x1 squared. Hold up. This should be minus x2 x1 minus x1 x2, but these commute since we're working with a square. So this should become x2 squared minus, oh, why did I put a minus? Plus x1 squared minus 2x1 x2. Now we're going to see what happens with distinguishable particles, the model of quantum mechanics we had approximately 15 minutes ago. Well, not 15, 25. And indistinguishable or identical particles, the model that we're currently working with. So with this, you probably can predict what's about to happen. We're just going to get x squared 2 plus x squared 1 minus 2 x1 x2. But with identical particles, everything changes. You know why? Well, with distinguishable particles, we are simply using the milquetoast wave function psi1, psi2. Here the wave function is psi1, psi2, well, psi1 x1, psi2 x2 plus minus psi2 x1, psi1 x2. When we plug in that there, some crazy stuff is about to go down. I'm forgetting how the conjugate applies to this. So let's see. What we get here is psi plus minus conjugate. And what is psi plus minus conjugate? Well, that's psi1 x1. Hold up. I have to rederive the basic laws of conjugation from scratch. 1 second. So let's say C is equal to AB, or A3 plus B3I is equal to A1 plus B1I times A2 plus B2I. So then what's the conjugate of this? Well, that means A3 plus B3I is equal to, okay, so AB conjugate multiplied by AB is equal to the magnitude of AB squared, which is just the magnitude of A squared times the magnitude of B squared. That's simple. So you get AB conjugate is equal to the magnitude of A squared over A times the magnitude of B squared over B. So AB conjugate is equal to A conjugate B conjugate. Okay, that's nice. So we get psi1 conjugate, or psi1 x1 conjugate, psi2 x2 conjugate, plus minus psi2 x1 conjugate, psi1 x2 conjugate. And so now what happens when we distribute that with, why is there an I here? Psi1 x1, psi2 x2, plus minus psi2 x1, psi1 x2. Well, we're about to get 4 very large terms. This multiplied by this, which gives us psi1 x1's magnitude squared. This times this, which is psi2 x2 magnitude squared. And then we have the interference term, which is when we multiply this thing with something that doesn't go along with it, plus minus psi 1 x1 conjugate psi 2 x1 not conjugate, psi 2 conjugate x2 conjugate psi 1 x2. And then we have the other interference, the other interference term, which is what happens when we multiply across this diagonal. So you get plus minus psi 2 x1 conjugate psi 2 x2 psi 1 x2 conjugate. And then you have the default term, which over here is just going to be, hold up. Okay. And then you have the default term, which is going across this. Okay, yeah, this is the default term, this is the interference term, sorry. Psi 2 x1 squared, psi 2 x2, psi 1 x1, psi 2 x2 squared. So, this actually reduces to 3 terms instead of 2. Hold up. Hold it. Hold on. Yeah, I'm dumb. This is psi 2x1, this is psi 1x2. Alright, so we still get 4 terms. It's not as nice as I thought it was. And so this is nasty, but we can work with it. And so what does it give us? Well, notice that when we were working with the previous version, psi was just well, what are we getting? Oh, I have to look at it. This one's not very smooth for some reason. Okay. Once we have this, where do we go with it? Now that we have this giant conglomeration of unhappy things. Well, we're going to have to... We were taking the integral of, remember, so we're trying to find x2 minus x1 squared. So it's going to be the integral of x2 squared multiplied by psi plus minus psi plus minus conjugate. And so, now that we have that, what else is there to do except, well, integrate. Finish the job. We get... Oh, God. Hold on. I'm gonna work using the top board, but there's no eraser. Okay. Wow, just touching this thing. Totally. Ugh. Okay. So you can take this back, and this gives us what? The integral of x2 squared psi 1 x1 squared psi 2 x2 squared plus x2 squared psi 2 x1 squared psi 1 x2 squared, then plus minus, these terms are a little bit deadly. Now, it turns out for these terms cancel out, and we are left with half x1 squared plus x2 squared. And, of course, as you'd probably expect, since x1 and x2 are not differentiable, well, not distinguishable, that means these two have to be equivalent, and so x1 squared, so almost having fun for a second. X1 squared is equal to half x squared 1 x squared 2. And so, with these guys, if you add them together, it almost looks like we're completed. It's going to be the exact same. Unfortunately, no. You might have expected it because of how messy it is, but 2x1 x2 gives us the standard minus 2x1 x2, but with a catch. The plus minus terms add on top of each other instead of subtract. And they tell us that, what's the term that comes after this? Oh, I forgot. But oh well. It tells us that since particles in real life, the same kinds of particle, are indistinguishable in quantum mechanics, bosons tend to get farther away from one another than fermions, which tend to have the expected value of that distance subtracted, which means they're going to get closer to one another. So, because of the indistinguishability of particles, this tells us already a huge amount of qualitative behavior of bosons and fermions. If we didn't have this, we would think bosons and fermions acted the exact same towards one another, whereas now we know there's a significant... If you take an electron and a proton, they can be in the same state because they are distinguishable. They are different particles. They have different charge, and they have slightly different masses, which means that, well, not slightly different. I think this is like 10 to the 15 times bigger than this. But regardless of what it is or what it isn't, since these two are distinguishable, we do not apply the plus minus stuff to them. They go with the regular thing. Where was it? Up here. x2 squared plus x1 squared minus 2x1 x2. Everything that we thought was going to work. No, that's not it. But if we have an electron and another electron, and this is going to tell us how bonds work in a few lectures, well, not in a few lectures, in the next lecture, the way an electron interacts with itself, because these two are identical, indistinguishable particles, is dictated by x1 squared plus x2 squared minus 2x1 x2 plus minus, it's dictated by this plus minus term. Or rather with a minus, because it's an electron specifically. Without knowing that these particles are indistinguishable, we lose a lot of the special flair that quantum mechanics has. So there it is. Identical particles are the most important part of quantum mechanics when we're discussing multiple particles at once. And they give rise very quickly to one of the most fascinating parts of quantum physics, the Pauli exclusion principle. Tomorrow, we're going to be studying atoms, how they bond with one another, and what a solid might look like for the first time, which means we're actually modeling things with quantum mechanics, very rudimentarily. See you then.
You want to end here?